In the first video in this series, we derived the Boltzmann distribution, which describes the probability of a system occupying a specific state of energy. In the second and previous video, we covered how the Boltzmann distribution leads to the equipartition theorem, which explains how every degree of freedom within a system gets an equal share of the energy. In this video, we're going to show what happened when an English physicist, Lord Rayleigh, applied the equipartition theorem not just to a system like a spring or a particle, as we've previously covered, but to electromagnetic radiation itself, and in doing so, showed that classical physics was fundamentally broken in what we now refer to as the ultraviolet catastrophe. One thing physicists already knew by the end of the 19th century was that when an object is heated, it begins to glow. At first it glows red, then orange and then white, and if it becomes hot enough it can even appear bluish. But what they didn't understand was why. Why does a specific temperature produce a specific colour of light? So, what is colour? Well, at this point they knew that light was a wave, and different colours were just different wavelengths. So they wanted to find an equation that related the temperature of an object to the wavelength of the light emitted at that temperature. To do this, maybe we make a graph that has the wavelength of the colour on the x-axis and the temperature on the y-axis. If we plotted the glowing orb here, we see this sort of curve forming. But that's not exactly how light really works. It isn't just one wave of a particular wavelength being emitted from the object. Instead, the object emits many waves at many different wavelengths. It's just that some wavelengths are more intense than others, depending on the temperature. So, if we were to plot the distribution of all the wavelengths coming from the glowing object, we would see that the intensity peaks at the colour that we perceive the object to be. This curve was actually measured experimentally by passing the light from a heated object through a prism or a diffraction grating, separating the different wavelengths out and measuring the intensity of each one. But the real challenge for physicists was using the theory to explain why this curve has this particular shape in the first place. Physicists such as Kirchhoff predicted that there must exist a function that takes in two inputs, the wavelength lambda and the temperature T, and returns the energy density U. What this means is that if we fix a temperature, for example an object at 4000 degrees, we can plot a curve showing how the energy density varies with wavelength. We can then choose a specific wavelength that corresponds to a specific point in this curve, which tells us the energy density at the wavelength of this temperature. If we change the temperature, the entire curve shifts, and if we change the wavelength, we simply move to a different point along the curve. So the question becomes, what is this function? To picture this, let's imagine that we heat up a square, and it emits radiation as it heats up, both outwards and inwards. And let's take a think about what sort of waves could exist within this square. Well, inside the box, the only types of waves that can exist are ones whose electric field vanishes at the boundaries, and those patterns are standing waves harmonics. This means that the allowed wavelengths are those that fit an integer number of half wavelengths into the box. So what happens if a wave doesn't fit neatly in the box? Well, here's an example of a wave whose endpoints are not zero. This type of wave cannot satisfy the boundary conditions imposed by the walls. When it hits the wall, it reflects. The reflected wave interferes with the incoming wave, and the result is that the field reorganises into patterns that do satisfy the boundary conditions, and a more complex wave like this is created. But here's the interesting thing. As Joseph Fourier showed in the early 1800s, any wave, no matter how complicated, can be written as a sum of simple sine waves. So even this messy wave can be broken down into a combination of these fundamental harmonics. As you can see, when we merge them together, these harmonics create the complex waveform. So this means that every bit of EM radiation within the cavity is simply a combination of the fundamental harmonic frequencies. Now we want to think about how the energy is distributed across these different waves. Let's take a particular harmonic, n equals 1, which we can call the first mode. We can describe the amplitude of the standing wave using a function, qt, which simply tells us the strength of the wave at time t. When qt is large, the wave has a large amplitude. When qt is 0, the standing wave disappears. And when qt is negative, the wave simply flips direction. Each mode has its own function, Qt. For higher modes, the wave oscillates more rapidly, so the higher the mode number, the faster the amplitude changes with time. We can express the energy stored in a particular mode in terms of Qt. From Maxwell's equations, the energy of the electromagnetic field depends on the square of the electric and magnetic fields. So for a simple mode, this means the energy can be written in terms of the amplitude Q and its rate of change, Q dot. The result is, the energy takes the form of a quadratic expression, one term proportional to Q squared and the other proportional to Q dot squared. So each mode behaves like a harmonic oscillator with two quadratic degrees of freedom, and the total energy inside the cavity is simply the sum of the energies at all these modes. The equipartition theorem, which we derived in the previous video, tells us that the energy is equally distributed across all quadratic degrees of freedom in a system. Each quadratic degree of freedom has an average energy of half kT, where K is the Boltzmann constant and T is the temperature. Since each mode contains two quadratic terms, Q squared and Q dot squared, it has two quadratic degrees of freedom. Each contributes an average energy of half kT, so adding them together gives an average energy of kT for every possible mode. So the total average energy in the system would be the average energy in the first mode, kT, plus the average energy in the second mode, kT, plus the third, plus the fourth, plus the fifth, sixth, seventh, eighth, and so on. But the number of modes that can exist inside the cavity never ends. It's infinite. And since each mode contributes the same average energy, the total energy of the system would also be infinite. But what does that mean? Well, let's imagine that a cavity gets heated up to 100 kelvins. The average energy of each mode in which the energy can be distributed within the system is kT. The total value of average energy in each mode, in this instance, would be 1.38 times 10 to the minus 21 joules. So to find the total average energy in the entire system, we add up this average per mode. But there's an unlimited amount of modes, so that would just give us an infinite amount of energy. This shows us that classical physics can't be working, since infinite energy is obviously impossible. Sounds like a complete catastrophe, right? So why is it called the Ultraviolet Catastrophe? Well, that's because Lord Rayleigh did some more thinking to figure out exactly where the physics started to break. Rayleigh began by imagining a cavity of length 1 metre and considering the different standing wave modes that could exist inside of it. Each mode corresponds to a single frequency, and conversely, each allowed frequency inside the cavity corresponds to one particular mode, one way that the energy can be distributed. This might seem obvious, but it leads to an interesting result. If we plot the number of modes per frequency against the frequency itself, we find that it's the same everywhere. Whether the frequency is small or large, there is always exactly one mode corresponding to that frequency. And since the average energy per mode is the same for each mode, kT, each frequency corresponds to the same amount of energy. But real waves do not operate in just one dimension, so let's imagine them in 2 dimensions. Here's an example of a 2-dimensional standing wave operating at mode 1, 1. In 2 dimensions, something interesting begins to happen as the mode numbers increase. When we move up to mode number 2, we suddenly see several new modes appear. Mode 1, 2, mode 2, 1, and mode 2, 2. How does that work? Well, if we take the mode 2, 1 and look at it along one direction, the wave behaves like a mode 2 wave in one dimension. But if we take a look at it along the other direction, it behaves like a mode 1 wave. So in 2 dimensions, each mode is really a combination of 2 one-dimensional modes. As we move to higher mode numbers, the number of possible ways of arranging these modes continues to increase. There are simply more possible combinations of nx and ny. If we stack the number of possible modes at each level, it starts to form a pyramid-like structure. And as the mode number increases, the number of possible configurations grows larger and larger. An even clearer way to visualize this is using what we call mode space. We place nx on the horizontal axis and ny on the vertical axis. Each point on this grid represents a possible standing wave mode. Now, here's the interesting part. A fixed frequency does not correspond to just one point anymore. For example, the same frequency could correspond to the mode 1, 5, or 5,1, and in fact it could correspond to any combination of nx and my that lies in the same circle. So instead of thinking about individual points, it's helpful to draw a circle in this mode space. The radius of this circle represents the frequency of the wave, and the number of lattice points lying around this circle represents the number of modes that can exist at this frequency. Now here's the key observation. The circumference of a circle is proportional to its radius, and since the radius here is proportional to the frequency, that means the number of modes available at that frequency also grows proportionally to the frequency. So in 2 dimensions, the number of modes increases linearly with frequency. And since the average energy contained within each mode is the same, kT, this means the energy density associated with each frequency also increases proportionally with the frequency. So now let's consider the real situation, where waves operate in 3 dimensions. Here's a representation of a 3-dimensional standing wave at mode 1, 1, 1. As we move up to the second mode, the number of possible configurations increases dramatically. For example, consider the mode 2, 1, 2. If we look at one face of this wave, we see a 2-dimensional pattern operating at mode 2, 2. Looking at another face reveals a pattern corresponding to mode 1, 2. And the third direction gives us a pattern corresponding to 2, 1. As the mode numbers increase, the number of possible configurations grows rapidly. There are simply more ways for the wave to be arranged within the cavity. A useful way to visualize this is to plot the modes in a 3-dimensional mode space, with axes nx, ny, and nz. As these axes expand, we see that the number of possible modes increase very quickly, because the system now occupies 3 dimensions. Now, imagine drawing a sphere in this mode space, where the radius of the sphere is proportional to the frequency of the wave. The number of possible modes for that frequency corresponds to the number of lattice points lying along the surface of that sphere. And since the surface area of the sphere is proportional to the square of its radius, we find that the number of modes at a given frequency grows proportionally to f squared. So if we plot the number of modes per frequency against the frequency itself, we see a quadratic relationship. The higher the frequency, the more possible modes exist, growing proportionally to the square of the frequency. And since the average energy contained in each mode is the same, kT, the energy associated with each frequency also grows quadratically. Now, let's take a closer look at what this prediction implies. If we express this prediction in terms of wavelength instead of frequency, we obtain a curve describing how the energy should be distributed across different wavelengths of light. But something clearly goes wrong. As the wavelength becomes smaller and smaller, the predicted energy diverges towards infinity. When we compare this theoretical prediction with the experimental curve we saw earlier, the two look very different. At longer wavelengths, the theory works quite well, but as we move towards shorter wavelengths, particularly in the ultraviolet region, the theoretical prediction rapidly diverges from what the experiments actually observe. This breakdown of classical physics became known as the Ultraviolet Catastrophe. And this was the crisis that ultimately gave rise to the field of quantum physics, when Max Planck proposed a revolutionary explanation for why classical physics failed when describing radiation. We'll explore that idea in the next episode, where we introduce Planck's quantum hypothesis. Thanks for watching, and we'll see you in the next one.